Hello everyone, I am Kulpreet Kaur from BSc Chemistry Honours final year. Today I am going to prepare an audio recording for visually impaired student on the topic of ion exchange chromatography. If a mixture of two or more different cations B, C, etc. is passed through an ion exchange column, and if the quantities of these ions are small compared with the total capacity of the column for ions, then it may be possible to recover the absorbed ions separately and constitutively by using a suitable regenerating solution. If cation B is held more firmly by the exchange resin than cation C, all the C present will flow out of the bottom of the column before any of B is liberated, provided that the column is long enough and other experimental factors are favorable for the particular separation. This separation technique is sometimes called ion exchange chromatography. Its most spectacular success has been the separation of complex mixture of closely related substances such as amino acids and lanthanides. The process of removing absorbed ions is known as elution. The solution employed for elution is termed the elutant, and the solution resulting from elution is called eluate. The liquid entering the ion exchange column may be termed the influent, and that liquid leaving the column is conventionally called the effluent. If a solution of a suitable eluent is passed through a column charged with an ion B, the course of the reaction may be followed by analyzing continuously the effluent solution. If the concentration of B in successive portions of the eluate is plotted against the volume of the eluate, an elution curve is obtained such as shown in the figure 7.1. It will be seen that practically all the B is contained in a certain volume of liquid, and also that concentration of B passed through a maximum if the ion exchange column is loaded with several ions of similar charge B, C, etc. Elution curves may be obtained for each ion by the use of appropriate elutants. If the elution curves are sufficiently far apart as 7.2, a quantitative separation is possible. Only an incomplete separation is obtained if the elution curves overlap. Ideally, the curves should approach a Gaussian distribution, and excessive departure from the distribution may indicate faulty technique and or column operating condition. The rate at which two constituents separate in the column is determined by the ratio of the two corresponding distribution coefficient, where the distribution coefficient is given by the equation. Kd is equal to amount of the solute on resin upon weight of resin in gram, amount of solute in solution upon volume of solution in milliliter. The distribution coefficient can be determined by batch experiments in which a small known quantity of resin is shaken with a solution containing a known concentration of the solute, followed by analysis of the two phases after equilibrium has been attained. The separation factor alpha is used as a measure of the chromatographic separation possible and is given by the equation. Alpha is equal to Kd1 upon Kd2, where Kd1 and Kd2 are the distribution coefficient of the two constituents. The greater the deviation of alpha from unity, the easier will be the separation. For normal laboratory practice, a useful guide is that quantitative separation should be achieved if alpha is above 1.2 or less than 0.8. An important relationship exists between the weight distribution coefficient and the volume of elutant V maximum required to reach the maximum concentration of an eluted ion in the effluent. This is given by the equation. Vmax is equal to Kd V0 plus V0, where V0 is the volume of liquid in the interstices between the individual resin bits. If the latter are spheres of uniform size and closed packed in the column, V0 is approximately 0.4 of the total bed volume Vb. The void fraction V naught upon Vb of the column may, however, be determined experimentally or calculated from density data. The volume distribution coefficient is also a useful parameter for chromatographic calculations and is defined as dV is equal to amount of iron in 1 milliliter of resin bed upon amount of iron in 1 milliliter of interstitial volume. It is related to the weight distribution coefficient by dV is equal to Kd beta, where beta is the void fraction of the settled column. It is also related to Vmax by the equation Vmax is equal to Vb bracket dV plus me beta. It should be remembered that the relationships given above are strictly applicable only when the loading of the column is less than 5% of its capacity. The application of these parameters may be illustrated by the following example. Example, a mixture of calcium 0.05 mol each of chloride and bromide ions is to be separated on an ion exchange column of length 10 cm and 1 cm square cross section using 0.035 m mole potassium nitrate as the elutant. The distribution coefficient Kd for the chloride and bromide ions respectively are 29 and 65. Separation factor alpha is equal to 65 upon 29 is equal to 2.24. This value indicates that a satisfactory separation could be achieved, and this is 196. Is confirmed by calculation of the Vmax values for the appearance of the chloride and bromide peaks. From the column dimensions, the bed volume is Vb is equal to 10 cm into 1.0 cm square is equal to 10, and the void volume beta is equal to 0.4. V naught is equal to 0.4 into 10.0 milliliter is equal to 4 ml. Hence, for the chloride peak, Vmax is equal to Kd V naught plus V naught is equal to 29 into 4 plus 4 is equal to 120 ml. For bromide, Vmax is equal to 65 into 4 plus 4 is equal to 264 ml. The relatively large values of Vmax indicate, however, the separation will be lengthy and the elution bands broad, particularly for the bromide band. The use of a more concentrated solution of elutant significantly reduces the values of Vmax and the elution bands become much sharper. Thus, the distribution coefficient for bromide using a 0.35 m potassium nitrate solution is 6.5, and using the same column Vmax is equal to 6.4 into 4 plus 4 is equal to 30 ml. In many cases, the efficient separation of mixture by ion exchange chromatography requires that the elutant concentration be changed during the course of the elution. This may be done in a stepwise manner or by continuous change in concentration as in gradient elution. The latter procedure can be carried out using simple laboratory equipment. A comprehensive discussion of the technique and of gradient elution devices is given in the view by L.R. Cinder. A more recent development, however, is the use of microcomputer control system for gradient elution. Example, for the separation of amino acids by ion exchange chromatography. The scope of separation by ion exchange chromatography may be extended by using for fixation or for elution or a solution capable of complexing the ions exchange. The formation of complexes may exist separations by diminishing the concentration of free ions and also by producing complexes of different stabilities, thus leading to significantly different behavior with selected elutants. The result of ion exchange separation may be influenced by varying the pH, the solvent or eluent, the temperature, the nature of the ion exchange resin, the particle size, the rate of flow of elutant, and the length of column. Ion chromatography. Ion chromatography is a relatively new technique pioneered by Small et al. And which employs in a novel manner some well established principles of ion exchange and allow electrically conductance to be used for the detection and quantitative determination of ions in solution after their separation. Since electrically conductance is a property common to all ionic species in solution, a conductivity detector clearly has the potential of being a universal monitor for all ionic species. A feature of ion exchange chromatography is, of course, that ionic solutions are used as eluents so that the eluted species are present in the electrolyte background. The problem which now arises in the application of electrically conductance for quantifying eluted ionic species may be illustrated by the simple example of the separation and determination of sodium and potassium in a sample in which these are only cations present. Complete separation of these two cations may be achieved using a strong acid cation exchange resin with aqueous hydrochloric acid as eluent. However, the high conductance of the hydrochloric acid is the influent effectively swamps the lower conductance due to the sodium and potassium ions, so preventing their measurement by electrical conductance. In IC, this problem of electrolyte background is overcome by means of eluent suspension. This thus is in the above example of sodium and potassium analysis. If the effluent for the separating column is passed through a strong base anion exchange resin in the hydroxide form, the following two processes occur. Neutralization of the hydrochloric acid HCl plus OH negative resin, chlorine plus water. Second is NaCl KCl plus OH negative resin, NaOH KOH plus chlorine negative. A consequence of these ion exchange process is that the sample cations are presented to the conductivity detector not in a highly conducting background but in a very low conductivity of deionized water. It may be noted here that deionized water is not always the product of eluent suspension. The essential deionized water is not always the product of eluent suspension. The essential feature being that a background of low electrical conductivity is produced. Analogous schemes can be devised for anion analysis in which a case is strong acid cation exchange resin is employed in the suppressor column. Ion chromatography permits the determination of both inorganic and organic ion species, often in concentration of 50 mu Gl negative or less. Since analysis time is short and sample volumes may be less than 1 milliliter, IC is a fast and economical technique. It has found increasing application in a number of different areas of chemical analysis and particularly for the quantitative determination of ions. The state of the art has been reviewed. A flow schemes for the basic form of ion chromatography is shown in the figure 7.3, which illustrates the requirement for simple anion analysis. The instrumentation used in IC does not differ significantly from that used in HPLC, and the reader is referred to chapter 8 for details for the types of pump and sample injection system employed. A brief account is given here, however, of the nature of the separator and suppressor columns of the detectors used in ion chromatography. Separator column. The specific capacity of the separating column is kept small by using resins of low capacity. For example, low capacity ion exchangers have been prepared by surface agglomeration method in which finely divided anion exchange resin is contacted with surface sulfonated styrene divinyl benzene copolymer. The small particles of ion exchanger are held tenaciously on the positively charged surface of the sulfonated beads. These resins are stable over a wide range of pH, in which respect they are superior to glass or silica based pellicular resins. Suppressor column, where electrically conductance is used for detection of sample ion in the effluent from the column and eluent background of low conductivity is required. The function of the suppressor column is so converted eluent ions ion exchange flow scheme chromatography flow scheme into species giving low or zero conductance. Example where NaHCO3 is used as eluent for ion analysis. This is converted into a background of dilute carbonic acid by using a strong acid suppressor resin. The low concentration eluents used to separate the sample ions on the separator column allow a substantial number of samples to be analyzed before the suppressor column is completely exhausted. The low concentration eluents used to separate the sample ions on the separator column allow a substantial number of samples to be analyzed before the suppressor column is completely exhausted. Clear and important practical consideration is the need to minimize the frequency of the regeneration the suppressor column and for this reason, the specific capacity of the column is made as large as possible by using resins to moderate to high cross-linking. Some instruments contain two suppressor contains in parallel, thus allowing one column to be regenerated while the other is in use. A more convenient arrangement, however, is the use of hollow fiber suppressors such as that developed by Dinox Limited, which allows continuous operation for the ion chromatograph. In the case of anion analysis, the suppressor incorporates a tubular cation exchange membrane which is constantly regenerated by dilute sulfuric acid flowing through the outer cases. It is appropriate to refer here to the development of non-surpassed ion chromatography, simple chromatographic system for anions which uses a conductivity detector but requires no suppressor column has been described by Fridge and co-workers. The anions are separated on a column of macrophores. Anion exchange resin which has a very low capacity so that only a very dilute solution of an aromatic organic acid salt is required as the eluent. The low conductance of the eluent eliminates the need for the suppressor column. The separated anions can be detected by electrical conductance in general. However, non-surpassed ion chromatography is an order of magnitude less sensitive than the surpassed mode. That's all about the ion exchange chromatography. Thank you so much.